Hi, chemistry students. To wrap up this mechanism case study, let's actually solve the problem. The earlier video was about, of course, describing that equilibrium first step, but we're going to do something a little bit different here, and we're actually going to solve it right from the get-go. So when you see a mechanism problem in Chem 1212, this Gen Chem problem, there's really only one way to go about it. And we're going to assume that our mechanism is going to be given some added information, not just the steps, but also how fast the steps go with relation to one another. And our goal is to find the step in the mechanism which is called the rate determining step. And for us, that rate determining step will always be the slow step. So the first thing we're going to do is, one, find the rate determining step. So the rate determining step, and we see that that's step 2. The second thing is we can immediately write down the rate law for that step. So for this particular case, the rate law is going to be rate is equal to K2, because it's the second step, times N2O2 to the first power. Why? Because it has a stoichiometric coefficient of 1, times O2 to the first power, because it has a stoichiometric coefficient of 1. So just to remind you, the reason that I can do this, the reason that I can use the stoichiometry is these are elementary steps. So when it's elementary, we have this ability to write the rate law from the stoichiometry. For a bulk reaction, we don't have that opportunity, and we have to actually go about using experimental data to find the rate law. So now that we have this, the next step is to look for intermediates. And we're going to look for them in our rate law. And if we have any intermediates, we have a problem, because rate laws cannot have an intermediate in them. So our goal is to see if there's one in there, and that would invalidate the mechanism unless we can find a way to work around that. So if we take a look at our mechanism right here, here's our entire mechanism given to us, then we see that N2O2 is actually one of these intermediates. So if it's an intermediate, we have a problem, and that is that N2O2 is in there, and we might have to just say that this is a bad mechanism. However, the equilibrium step gives us a neat little trick that we can deal with. And that is, if there is an intermediate, we're going to look for the equilibrium to help us out. And our goal there would be to use the equilibrium to substitute away from the N2O2. So to get a little bit more definite on that, what we're going to do is we're going to look at the equilibrium real quick. And the equilibrium says that K1 over K minus 1, the rate forward divided by the rate constant in the reverse, is equal to the products raised to their stoichiometric coefficient divided by the reactants raised to their stoichiometric coefficient. And since there's two NOs, that would be NO squared. What this means is I can just use some algebra here, and I can solve for N2O2. It's equal to K1 over K minus 1 divided by, or multiplied by, NO squared. So what this means is I have a rate law that has N2O2 in it, and I now have an expression that has that relates N2O2 to other chemicals involved with this reaction. So I'm just going to directly substitute this right in for that guy. The way it works is this. I say that rate is equal to K2 times N2O2 and O2. There's my rate law from my mechanism, but I'm going to substitute in for this. So I'm going to have my K2, then I'm going to have my K1 over k minus 1 NO squared multiplied by the O2. So if we can do this, then we're going to substitute for the intermediate. Once we're done doing this substitution, which we've just finished, our last step is to compare to experimental rate law. So to get the experimental rate law here, we have to go back up to the problem, and it says that it's second order in NO and first order in O2. So experiments show this to be true. Therefore, our experimental rate law is, the experimental rate law is equal to some constant k times, it says NO squared, n to the second power, and O2. And our rate law is, rate is equal to K1, K2 divided by K minus 1. Don't worry about the order in which you multiply things. Times NO squared times O2. And if you think about this, these constants right here and right here, they must be equal to each other because the rest of it is the same. These are identical. Therefore, we've been able to show that our experiment matches our theory. And what we now have is a valid mechanism. It adds up to the overall reaction, and it also matches our experimental rate law. Putting those two things together means it's a valid mechanism. And just a reminder, valid does not mean it's the mechanism. There may be more than one mechanism that I can write that is valid. So there we have it. Our rate law, our mechanism matches the rate law, and so we're going to say this is a valid mechanism, and we'd have to do more experiments to get more information, but this is as far as we would go in a Gen Chem 2 class. Hope this helped you out.